Excellent. Welcome, everybody, and thank you, Joe, for the introduction. Thank you, everyone, for being here. It's an honor to present. As you heard, I'm from Netflix and from the Online Data Stores group, and the problem I'm going to talk about is one we've solved at Netflix, one that we think other companies are likely facing and will have to solve or have solved in some way. And I'm going to talk about the system that we've built. I'm going to talk about the kind of architectural choices we made. And I think that this is particularly relevant to the SREcon because the kind of architectural decisions we made and the trade-offs we faced really skew towards the operational side. So we had to think a lot about how we're going to operate this new system, and we had to make trade-offs, some of which increased our kind of operational load, but made other things easier, as I'll kind of get into. So let's start with what is our fundamental challenge we're trying to solve. And that is that we have this data offline, things like ML features, pre-computed indices, or you can imagine there's many data sets of this shape. And these are computed and assembled offline, but we want to serve them online. We want to serve them with low latency in the hot path when we make queries to serve our users videos, and when they log in and everything else in that line. So the system that we use, the team I work on is the key value team. So the system that we're working on here is a key value store. And I'll give a quick kind of overview of what we had coming into this project. And that's this kind of key value abstraction, which is not any given database, but rather just an interface over the kind of concept of key value. And Netflix has, especially the data platform, has really leaned into abstractions. And many of my colleagues have talked about this and written blogs about this. So there's a lot of content on this particular topic, and I'll talk about how it's relevant for us as well. And one thing you'll notice is that this middle layer, this API layer, is stateless. And in our original build of the key value system, statelessness of the API layer was something that we kind of built into the system, and we relied on other existing databases like Cassandra to provide us the persistence layer. And as we evolve this system, we kind of start to challenge that fundamental piece. So okay, let's get back to our problem. We want to move all this data online. Why can't we just write it? We have a KV store. We can just call put over and over and over again. Why not just write this data to our mutable store? The problem is if you write enough, if you keep on sending 50 terabytes, 100 terabytes of data, eventually you're going to degrade any given store. You're not going to be able to support the throughput of all those writes, and then in fact that throughput will dwarf the actual capacity you need to serve the reads. So okay, you start to degrade your traffic, eventually you cause incidents. So this is not where we want to be as operators. So okay, fine, don't write that fast. Let's just back pressure the writes. That works, right? Now we can kind of safely serve things. I will say it's harder than it sounds. It's actually hard to do kind of perfectly safe back pressure in a kind of a resource-based way, but it's possible. And so this is something we looked at. But all of a sudden, you have kind of this fixed rate. And what if that fixed rate just isn't fast enough? What if as you load your data, you want to load too much data in too short of a time? Okay, again, now you're back to the first problem. You have to push your rate limits up, and you start to overload your database. Okay, well, let's just give ourselves more capacity. Can we just scale up? We can. We can just scale up. We can throw hardware at the problem. We can just spend more money. And that will get us somewhere, right? Now cases that we couldn't do before, we can do. But there's two problems here. The first is we're paying for this capacity at all times. So unless you have very flexible auto-scaling on your data stores, which is its own operational challenge, then you find that you have to scale your data stores to support the write throughput. And the read throughput, which is like kind of your real use case, is actually no longer driving your cost. So your cost is driven by the amount of data and how quickly you want to move that data. And you have these big troughs where you're just reading that data, but you're not kind of fully utilizing your system. The other point is even if you accept this kind of outcome, which is reasonable, there are systems that work this way, at certain scales, it's just cost prohibitive. So if you want to move enough data fast enough, the throughput you have to pay to write it all through Cassandra really is just extremely expensive, or it's at least not in the budget for the project you want to do it. So we come to this this trilemma. We have three things that we want, and we can't have them all. So if we just write everything, then okay, we have this risky situation where we overload the database. If we kind of give up on data freshness and back pressure everything, then it's hard to quickly write data, and the use cases, it might not work for your use case because you want to write data every day, but it takes you 2 days to write the data. All of a sudden, all your reads are stale. And finally, you can scale up and just spend money, but of course, that's a limit. Can we have all three of these? That's the question that we are trying to answer here. So towards that, let's think about what we're really doing when we write this data. A kind of key question we should ask is, why are we doing all this work? What is all this work we're doing when we write 1 million times per second to this database? What we're actually doing is reconstructing information that we already have offline. So KV is backed by Cassandra. What does Cassandra do? You take all these writes, you write them to SS tables, you compact those SS tables, and you end up assembling a structure, which is basically the data laid out and sorted, which you already know. Right? This is different from a normal database where you aren't sure what writes you're going to get. And so that's what Cassandra is designed to solve and does very well. But in this case, you already know the exact structure of the data you want to read. You have it offline, you already computed it. So you're really wasting time redoing these writes. And you're actually, it's even worse than that because you are breaking it down into all these little operations, one write at a time. And then you have to for each one, there's overhead, you have to reconstruct this big data set. Okay, what can we do with this? Right, so we already know this final layout. Why rediscover it in real time? This is kind of one insight. We can generate these tables offline, right? So we have it in some store like Iceberg, but we can still just compute in a kind of closed fashion the exact SS tables that we eventually want to serve online. And once we do that, now we have a very different sort of problem. We have these files that we are going to kind of deploy, and this is a problem that we're all very familiar with. You have a set of files, and you want to kind of rev new infrastructure with those files, not the old files. That's a lot like code deployments. So this is a kind of a mutable set of data that we're now spinning like a code deployment. That gets us into a very familiar world of tooling, of operations, and we can learn from how we've all learned to deploy code over the years and apply these same principles to deploying data. So, okay, first let's start with what the offline path really does. And I'm very lucky to work with some very talented and expert engineers on the data movement team who built this pipeline so that I don't have to think much about it. From my point of view, these files just appear materialized in S3. But under the hood, this is what happens. We have kind of offline data in Iceberg. We read it with Spark or other processors. We write it to RocksDB SST tables. We load it into S3. And then from there, I'll talk about the system that we've built around these kind of files based on those insights that we talked about to actually serve this in the hot path. So as I mentioned at the beginning that we have that stateless KV layer. One of the decisions we made going into this was to explore making that layer stateful. And that's a significant trade-off. So we have all these kind of sets of data and RocksDB SST tables, and we built a system that's so far mostly around kind of front and Cassandra, but now we're using the data set in a very fundamentally different way. The question was, why not take these data sets that we've assembled offline and just stick them on the disks of the API layer and read them right off the disk? We did that, but it was not an easy question. So as you can imagine, operating a stateless system is very different from operating a stateful system. So we gained some stuff, right? We solved that trilemma we were talking about. We have the CI/CD component that we talked about, and I'll get into more detail there. We decouple the loading and serving, and I'll show that in some detail. But we opt into all these things that are hard, all the things that make stateful systems hard, that make databases in some ways more complex than stateless systems. So we have to manage leases, right? Not every node is the same anymore. Nodes have different data. We can't have the whole data set on every node. We have to capacity plan in a much more kind of intricate way. We can't just have an auto-scaling group that scales up and scales down. We have to, every time you add a new node, that node has to have some subset of the data. That subset has some relationship to the other nodes in the system. So this capacity planning becomes much more complex. And then we need to route our requests to the right node. So in a stateless system, right, you can just use round robin, or there's many load balancing algorithms, but your core goal is just to balance load. In this case, there's a correctness element, right? If you are searching for a specific ID or if you're reading a specific ID, you have to send that to a specific node, right? Otherwise the data won't be there. So this is a kind of core decision point that we had, but we pushed through and moved towards a stateful system because of what we gained. And I'll talk about, I think, kind of one of the key components of why we were able to do that without adding a ton of complexity. But first, let's dive into what this complexity really was. Also, code deploys get harder. So first, leasing. This is a kind of a solved problem. Like, this is a very common problem, right? If you need a set of nodes to each own a piece of a data set, there's ways to do that. But these are often coupled to databases. So that while the techniques are there's kind of some, like we weren't able to just out of the box reuse Cassandra token rings. We had to kind of create something. But it ends up being that this is a very possible and kind of podded thing. So this was one of the things that seemed scary at first, was we have this new correctness element we're introducing to our formerly stateless system. And this almost seemed like a blocker, but if you explore it, it's actually something that's quite doable. And we were able to do it fairly robustly on top of just a kind of relational database using transactions. There are many other ways to do this. Systems like Zookeeper can do this, and there are practical reasons to go one way or another. But just to lay out what we're actually doing, if we have our serving fleet, you can imagine that each instance is responsible for some subset of the data. You can divide your data set into some number of groups, let's call them partitions, and then when a node comes up, it becomes responsible for that partition, and it has to go download all the data associated with that partition. And that's exactly how the system works. We have all the data staged in S3, a node comes up, it acquires a lease, and it goes and downloads the data associated with that lease. But this introduces another problem, which is how much data do you put on each node, and how do you decide which, exactly how to chop up your data set, exactly which data goes where. You get into this kind of complexity of capacity planning. And then it's made even more complex by some of the kind of practical limitations of very, very reasonable limitations, but still practical limitations of EC2, the platform we work with. So the first is that there's this chunkiness, right? Like each instance type has a specific amount of disk and a specific ratio of compute to disk. So you can't just say, it'd be great if I could chop my data set into exactly these instances and use exactly 90% of each disk, but it doesn't work that way. Of our use cases, the actual data to compute ratio varies. So there are some use cases that say, we have this huge data set and we want random access to small portions really quickly. There are other use cases that are more like almost like a traditional cache of like, I have this small amount of data, I just want it online, I want to be able to access it, and I want to access it a lot, I want to access it a little. There's kind of every shape that you can imagine of this ratio exists. And so, this makes the problem of picking across these chunky sort of allocations difficult. There's also the question of NVMe versus EBS, right? There's one kind of high-level trade-off, right? There's some fixed latency cost to EBS. But then there's also these cost trade-offs and planning trade-offs. EBS is very flexible, but as we'll get into, the cost profile doesn't make it perfect for every use case. So let's talk about how we approach this problem. This is actually open source. We have a capacity planning model we published, and we added we call it read-only KV model. So if you're really curious, please go take a look. But we have an algorithm that we call partition-aware sizing, where we compute kind of an optimal outlay of this data across our nodes, and then kind of do another pass to re-ensure that we reuse all the extra capacity that may have been left over in the shape we're forced into. So we can think about this kind of as a bucketing problem, right? So we have this amount of data divided into certain partitions. we know how many partitions we can fit on a given node. Let's say a node has a fixed disk size. And then we know, okay, if we can fit that much data on one node, we need, of this type, we need at least this many nodes. Okay, and then if we don't have enough cores with that layout to serve the data set, okay, let's add replicas, and then all of a sudden we can have more of each type and we can serve the data set. This is effectively the algorithm we run, and we just run through every instance type, every shape, and perform this math and come out to an optimal shape. The next key part, though, is if you have a compute-heavy data set, you'll end up with all this free disk because you requested, okay, I need so much compute to serve this. There's a chunky relationship between compute and disk. So if you get compute, you are getting disk with it in the non-EBS case. The key thing that we then can do is we can use that disk, not just waste it, by filling it with additional copies of the data. So we can increase our replication factor into like huge numbers. We can have data sets that are replicated 16-fold, and it's free to do. So this was a kind of fundamental shift in how we think about replication factor. Often when you're thinking about a database, you say, okay, I want 3 copies because that gives me sort of, that's the minimum to assure the availability I want. This actually works the other way. You have all this compute, you have all this disk lying around, you may as well use it. And so this was something that kind of really pushed our tolerance to failures up because we can have really highly replicated data. Okay, the second question is NVMe versus EBS in general. There's this kind of interesting relationship between the two. If you think about what EBS really does, it's decoupling the compute from the storage. So what this allows you to do is if you have a lot of storage and you don't need much compute, you can scale your EBS volumes high and keep pay for less compute nodes. This works when your savings on compute are sufficient to justify the increased spend on EBS, because per gigabyte, EBS actually ends up being more expensive than NVMe for certain instance types. And this works well, but there is this breaking point where eventually it's no longer worth it, and actually it's better just to pay for the NVMe. There's also just, in general, if you have so much data that the EBS cost dominates, then again, it's better to pick NVMe. So the point is, EBS sounds like it solves this problem, kind of, and we don't have to worry about the NVMe case because we can just decouple it and scale these two independently. And that does work in some cases, but at enough scale, you actually do have to start thinking hard about how you're going to allocate these kind of chunky relationships of compute and storage. Nice. Okay, let's talk about the next part here. So we have our data. Each node, we've picked how much data goes on the node. We've gotten a lease and downloaded it. Now we need our client to talk to those nodes. And again, there's a level of statefulness here, right? So if we send the request to the wrong node, the data won't be there. So we devised just a very simple scheme here where when we partition the data, we partition it by hashing and modding the ID. And so that each group of data has this relationship to each other via hash mod. We can recompute that same relationship on the query path. So when we make a query to a given ID, we compute the same hash, we compute the same modulus, and we pick our node. This diagram is slightly simplified because it's showing picking one node out of 3. In reality, you're picking a set of nodes, all of which have your data, and then you can round robin or load balance across those accordingly. Yeah, this does, I hand-waved away before the offline path as owned by our great data movement folks. This is one piece where we do have to integrate. So the way they partition the data and the way we tell our users how the data is partitioned has to be connected. Another kind of difficulty. So yeah, we get to this question of like, I've talked about all these difficult problems, or seemingly difficult problems. How have we not just built another database and kind of pushed so much complexity to our consumers? And I think the answer really is the KV abstractions. Netflix has really leaned into abstractions, and this is a version of that paying off, because the same user interface, the same client libraries were all reusable by all our users. They didn't have to know about any of this. All they had to say is, oh, I want a key value shard, and I'd plan only to do reads, and behind the scenes, we can kind of control all of this. So even though we are increasing the scope operationally, we're containing the scope to the platform. We're containing it to our team. One other thing to call out is this is useful for our team as operators as well. So we're not just introducing some kind of fully new service with new metrics and new libraries. This is built into existing services, existing alerting systems, existing observability systems. So as operators, my teammates are able to kind of take the knowledge they have of operating the key value system in general and reapply it to operating this system, which is just another variant of KV. Okay, so we've gotten to this point where we have all these challenges. We're able to at least hide them. So fine, but what does this buy us? Like, why even bother with this in the first place? And we gain a lot from it. The first is the idea of CI/CD for data. So, everyone's kind of familiar with these sort of blue-green patterns, but one thing that we can do that's very powerful is when we bring up our new data, our green server here, we can run effectively arbitrary validation on it, risk-free. So the offline team, for example, just produced this data set and we just loaded it. They know exactly what data should be there. They know what it should look like. They have some idea of how latent requests should be. We can really beat it up. We can send all kinds of requests. We can check schemas. We can check hashes, checksums. And we can gain a ton of confidence in this new data set before the production side ever sees it. But it's the actual serving layer that will be in production. So we're very close. We're validating something that's very close to what's actually going to be in production. And that's really useful. This gave us a ton of confidence in rolling this out. Like, there's a whole class of bugs that you can imagine of, like, some metadata gets mismatched and we don't download one of the SS tables and there's a data hole. We can actually especially because of our close integration with the right side, we can assert, oh, we did a read from a key that we know appears in each SS table and each one came back. So we must have downloaded at least part of each SS table. This kind of validation gave us like really, really enormous confidence in rolling out, and it does on every deploy. So on every deployment, we can continue to have this integration, this testing. So any regression can immediately stop the pipeline, and we can debug and see what happened. Once this passes, again, because we control our own serving layer, we can then cut the traffic over to our new, now validated deployment only once we're ready. And this is instantaneous. It's just like just as you would imagine a red-black happens in a normal kind of stateless system or any other system. Of course, this means we also can go the other direction, right? Let's say that we cut over the green and something goes wrong that we didn't detect. There are certain classes of issue that we can't detect that are even outside the correctness of the system. Maybe we deliver the right data, but for some reason there's a regression in the recommendation system. Like we notice impressions are going down or something like this, and the team that owns the data set wants to roll back. We can facilitate that, and we can do it effectively instantaneously. Again, it's just a DNS swap to move back to the warm standby. And it's like now a kind of last known version. It's very similar to the idea of a code revert, where you can just, I know this commit was good, something's going wrong, let's revert to that commit. That gave our users this kind of enormous freedom to experiment because the stakes of serving the new data set are low, right? If you imagine you had written all this data one by one to Cassandra, the rollback story is much more complicated. Yeah, no data reload. I think some people might be thinking now, this is great, but aren't you kind of paying for this data twice? You have this blue and this green server, and that's right. So there are trade-offs. If you keep the old ASG warm, you can immediately fall back to it, but it costs double. If you destroy and redeploy from S3, you can tear down the old ASG and you can recover, but you have to move the data back online. We support both, and we support this as a configurable spectrum of trade-offs. And each use case can decide based on basically their confidence, their criticality, how much they want to pay and what they get for that cost. So making this tunable, I think, is kind of a key thing. And again, this is something that we learned from code deployments. So code deployments use the same strategy. It's not at the same scale often because you can keep an old ASG around that's configured with the old code for cheap, but the idea is the same. let's see. Okay, the other thing that we really gain from this is this decoupling of two things that are of very different criticality, which is the serving and the loading. And this comes back to the triangle we had at the beginning, the trilemma we had at the beginning, where if you overload your server, you have this risk of degrading the availability of your online serving for reads while you're doing all these writes. And you might see an image like this where, okay, we're going along at kind of nominal CPU usage, just doing these easy reads. All of a sudden, we have this huge 80% spike and spike up to 80% CPU utilization. Reads might be degraded. And this is an image that looks a lot like what we saw in the Cassandra world before. And but this image actually is from this new system. The key thing, though, is that this is split into two, right? So there are two pieces of infra here. Hopefully you can see that well enough. There's this orange line, which is our old capacity, and you can see the CPU of the orange line never goes up. So this is just serving reads, and all of a sudden this new blue line appears, and it starts loading all the data. It shoots up, it saturates the disk, it saturates the network. We're working hard actually on pushing this even further to really fully utilize every available resource and move data absolutely as fast as possible. But the old service is completely uninterrupted because it's totally independent, it's totally different nodes. And so you can see then at 1530 or so, the switch happens and the CPU drops totally off for the old and jumps back up for the new. And the latency remains flat this whole time. And does that look flat? Almost flat. There's a little spike there. What is that little spike? You'll notice it's at the 1530 mark. And if I go back, that's actually not the time of the load, right? So during the load, it is totally flat. But during the time of the cutover, there's this little latency glitch. I left this in because it's kind of just an interesting fact about what that is. And we, in some cases, have worked to ameliorate this. In other cases, it doesn't matter. What that is that the new nodes, their page cache is empty. So the old nodes have the page cache warm. They're serving a large percentage of the reads out of memory, or at least some percentage of the read out of memory. When you hit the new node, nothing's in the page cache. We have techniques actually to pre-warm the page cache. Depending on the use case, it matters or it doesn't. But yeah, that's why that little bump is there. So, okay, we've gotten to this point where we really have made data deploys a lot like code deploys. We've been able to reuse this playbook of CI/CD, of rollout and rollback, of blue-greens, and we're using it not just for code that we're all used to, but we're using it for data itself, for the actual movement of data to online systems. The only cost is we have to do some of these things ourselves. We have to do our lease management, we have to do our own routing layer, we have to manage the stateful identity of nodes, but we get a lot out of it. That's kind of the key point. So yeah, this is just some numbers here about, so we had a data set before that we actually said we thought at our maximum budget it would take about a week to load. We can load in 30 minutes. We have 50 terabyte data sets that are moving weekly or daily. We have huge cost reductions in some of these clusters, kind of fleet-wide, that were overscaled to accept writes. And we can do hundreds of data deploys per day across several hundred or approaching thousands of data sets. And we serve this all with a P99 of less than 5 milliseconds because it's really quite fast, especially on NVMe with a big page cache. I mean, you can just imagine it's really ripping. It's great. So yeah, I'll take a moment here to summarize. There's some key lessons that we've learned here. The first is that the abstraction really enabled this. If we had no abstraction, if we were just had our clients connected to Cassandra directly, where in this pipeline could we have inserted this new system? This gave us a degree of freedom to pivot and kind of change the fundamental nature of our serving layer without having any impact on our clients, without having them need to learn anything new, rewrite any apps. We were able to onboard this system to existing consumers of our interface, and that's abstractions really paying off in ways that are hard to predict even ahead of time. It just shows the value of the idea. The second is how important familiarity is, and there's two pieces of this. The first is to our customers, right? So if you are if you're any developer at Netflix, you're familiar with how to deploy code, how to do CI/CD. You can now apply that same thinking to data, and that is a compelling story for our users. And they can think about how to write validations in the same way they think about how to write smoke tests, and that's kind of a powerful thing. And it's also useful for us as operators to build on our existing abstraction because it's so familiar that operationally it doesn't feel like, okay, now we have to just support this whole new thing that seems separate. It's more like we're supporting something we're very familiar with in a new mode, and that makes it easier for us to think about and to observe and to operate. The third is that statefulness often is talked about as something that's kind of daunting and maybe best avoided or best left to the database. And maybe in certain cases there's some wisdom to that, but it's a trade-off, right? There are some powerful things you can do if you just reach past that blocker and allow yourself to venture into the world of stateful systems. And there are some things that are actually not as hard as they first appear. So I think like we originally were facing this trade-off of are we adding just far too much complexity by adding yet another set of stateful systems here? And I think the conclusion of this project is that it's not. It's worthwhile. The benefits outweigh the operational costs. Nice. That's all from me. Thank you very much for your time and listening. And